So what did we learn? We know that quadratic functions get their quadratic nature from the x squared term. We know the simplest quadratic function is y equals x squared. We realize that the x is our input and the y is our output. We know how to plug in numbers for x and solve them for our y. And we know that when we do that, we end up with coordinate points. We are comfortable with the basic pattern of y equals x squared because we know our perfect squares. 3 times 3 is 9, 4 times 4 is 16. We're also comfortable with the fact that it mirrors, it reflects the same number outputs on either side. We also saw what happens when you put a coefficient with your x squared term and how to always remember that the exponents go before multiplication. So you always square your x before you times by 2. We also noticed that the pattern of the outputs compares nicely to the pattern of our original y equals x squared. In this case, all the outputs are doubled because x squared is being times by 2. We tried this out on several functions, and we noticed the same thing. The outputs are all just multiplied by 3, and the outputs are just multiplied by 10. We also learned that negative x squared is actually negative 1 times x squared. Therefore, the x squared happens before multiplying it by negative 1. This keeps us from accidentally making positive numbers, thinking that the squared goes to the whole negative 5, which it doesn't. And so we ended up getting with a negative version of our original. 2 more strange things we have seen are fraction coefficients, which actually, instead of making our outputs larger by like doubling or tripling them, it cut them all in half. So 9 became 4 1/2, 4 became 2, etc. The last thing we saw was instead of multiplying the x squared term by something, we're actually going to add 1 to the x squared term this time. So instead of shifting all of these through multiplication, we shifted the original pattern up 1 with addition. So 9 became 10, 4 became 5, etc. This also shows us that quadratic equations can have constant terms. And we'll see later they can also have regular x terms. They just have to have an x squared term or they won't be a quadratic. We summarized all of the tables we found, even though we shortened it to not go up to 5. And we see the patterns in here and how they all relate to y equals x squared. Actually call y equals x squared the parent function. So the parent quadratic function, because every other quadratic function is based on the pattern of y equals x squared. We also reminded ourselves that if we can create tables of x comma y input-output pairs for all of these different functions, then we could graph them, because every x comma y is a coordinate point. So we tried graphing y equals x squared by using the table to get coordinate points. And by carefully graphing all those coordinate points, we started to see the U shape that mirrors through the center. And this U shape is called a parabola. And by checking very small numbers between 0 and 1, we were able to graph what the parabola looks like much closer to the origin. And we can see it's much gentler and smoother and gets more gradually flat. And it is completely flat at the origin on this function. We also connected the mirror pattern of the U to the mirror pattern of the outputs. Now we will go on to explore one of the most depressing parts of all of algebra,